Good morning, everybody. Hopefully everybody's doing well. Looks like a few of you are still trickling in, so we'll just get started really slowly and then everyone kind of work their way in. Thank you for the green check marks. And this is our last class before March break, which is kind of crazy when you think about it. We've been kind of cruising along here pretty good, and we're in a great position going into March break in terms of the material we need to cover after the break. And, we're doing okay. So nothing to be concerned about in terms of pacing. One thing I am concerned about is a lot of us are still trying to make it through all that biology stuff, which kind of scares me going into the break, because if you're not ready to, continue on after biology, you're just simply not going to make it in time. So we have tons of material to get through in terms of chemistry and physics, so there's lots left in the course. Mrs. Wood never came to our other class, so that might be why some people aren't here yet. Oh, okay. So Mrs. Wood didn't check in with you guys this morning. I'm not sure. I haven't even seen her. I don't even know if she's here. But it doesn't matter. We're going to just go on. And if people want to watch the recorded video later, they know how to do that. So thank you for being here, I guess. All right, a couple things. We went through about halfway through this section 10.2, last day earthquakes and volcanoes. And it isn't really a section in the course, but I think it's really interesting. So I will make sure that we just talk about some of the things that I find interesting, because I think it's worthwhile to talk about some of these things. They're pretty cool, exciting sort of stuff that happens with the world around us. We're going to start a new unit, Alex, on, I think we have class on the Wednesday or Tuesday after the break. So we're going to start a new unit, unit 4, I should say, after March break. So we're just going to continue on, finish off this earthquake and volcano stuff. We're going to look at the earthquake simulator and how to kind of navigate through that today. And then that's it. There's not a whole lot left, only a couple pages of the notes. So let's just do this. I'll just flip through, kind of recap where we went through last day. So we talked about earthquakes and where they happen, and they're at these plate boundaries. We talked about the Ring of Fire. Why the oldest island of the Hawaiian Islands is the smallest, because of weathering, remember that. And then we talked about Yellowstone, and there was actually an interesting story I was reading. If you've seen in the science course on the right side, there's a bunch of news headlines. There was a news article I was reading about the Yellowstone and why it's a hotspot and why it exists there, and it turns out that they have this theory that this Pacific plate that was getting subducted under the North America plate is still kind of being subducted and kind of rising up in that spot. That is what was interesting in the article, that they're still trying to figure out why exactly that hotspot is where it is. Then we talked a little bit about seismic waves, and we're going to continue on that. And let's just jump right into seismometers. So this is where we left off last day. So we'll finish off the notes, and then we'll take some time to look at the earthquake activity that's built into the course, which is also part of your learning guide. And then I'll give you guys a chance to go through that, and then I'll answer any questions you might have if you're running into problems. And that's it. There's nothing really pressing to get through here today. It should be pretty quiet and pretty easy. So what's going to be on the midterm, Ava? That's a good question. The midterm, I believe, is April 14th. I think we sent that out to you guys. And April 14th is the midterm. It'll be for sure the biology stuff. So units 1, 2, and 3. There'll also be unit 10. And we'll probably make it through unit 4 before then. So just a little bit of everything we've covered up until April 14th. And I'll make it very clear where the cutoff is. Hopefully there's some sort of natural cutoff that we run into. And I'll say, okay, everything we've learned so far is going to be on the midterm. So that's April 14th, if I'm not mistaken. All right, so A seismometer is an instrument that scientists use to record how much earthquakes shake something, essentially. And they can record horizontal motion as well as vertical motion. And there are thousands of them all over the earth. They're at the bottom of seafloor, on land. Some universities have their own seismometers. They put them next to volcanoes to figure out when volcanoes are likely to erupt. If people live nearby, they put them next to big fault lines like the San Andreas Fault, figure out if there's lots of little earthquakes. That's a good thing. That means the plates are moving. If there's no seismic activity for a long period of time, scientists get worried because those plates have locked and energy's building. It's building, and then eventually they're just going to slide and you get a really big earthquake. So we'll talk a little bit about the Richter scale. I'm sure a few of you have heard of the Richter scale before. And we're going to spend kind of the majority of time talking about the different waves, the P wave and the S wave, and how they travel at different speeds. So the analogy I used last day was when you're outside in a lightning storm or in your house, you see the flash and then you don't hear the sound until a few seconds later. Now, the flash and the sound originated at the very same instant in time, but because light travels so much faster than sound, it's about 1,000 times faster than sound, you see the light first, and then the sound takes a while to make it to you. Same idea with P and S waves. The P wave and the S wave are created at the same time, so the closer you are to the epicenter or the focus of the earthquake, the closer together the P and S wave will be. If you're a long ways away, that P wave's traveling so much faster than that S wave, the distance between them is a lot longer. So here's an example of what that looks like on the graph here. You can see that the distance you are away, so this is in 1,000 kilometers distances, the distance you are away, the longer the time between the P wave, the S wave, and then the L wave, which comes later. Remember, the L wave is the love wave, or the last wave if you want. P wave primary, S is secondary, L last. That makes sense. You can think about it that way. All right, so let's look at a few ways which we can use this information. So we talked a little bit about the layers of the Earth and how we know that the center of our Earth, the core, is solid, and then the outer core is liquid because those S waves get blocked by it. And we know that S waves can't travel through the liquid. So when you have these seismographs all over the world, they're all over the surface of the world, there's thousands of them all over the place. When an earthquake happens somewhere, you pick up the readings, and if you get a reading, like right down here, if you got a reading that didn't have an S wave, you'd know that the earthquake's actually occurred on the far side of the Earth. And these seismic stations are accurate or precise enough to measure earthquakes all around the world. So generally speaking, when an earthquake gets released in the Earth's crust somewhere next to one of the plates, it's picked up all over the world. And we'll look at some interesting things that happened as a result of that. So talking about the Richter scale, it's kind of a difficult concept to wrap your head around because you're probably not used to talking about something in a logarithmic scale. So when we say a logarithmic scale, what does that mean? Well, it means that everything on the Richter scale is measured, generally speaking, all of earthquakes that we experience will happen from about 0 to 10. So 0 to 10 seems like every earthquake can be measured there. Why can't we have an earthquake that's 20 or 100 on the Richter scale? Well, each step on the Richter scale is it represents 10 times the strength of the previous step. So if you had an earthquake that measured, let's just look at like a 3 on the Richter scale right here, a 3. And then you had an earthquake somewhere else that measured a 4. Well, it turns out that the second earthquake that was 4 is actually 10 times as strong as an earthquake that's 3. Now, what happens if you take 2 steps on the Richter scale? So if you had an earthquake that's 3 and you compared it to an earthquake that was 5, well, the first step is 10 times stronger, and then the second step is another 10 times stronger. So you're looking at 100 times. So if you do 3 steps on the Richter scale, you're looking at 10 times 10 times 10, so it's 1,000 times. If you're looking at 4 steps, you're looking at 10,000. 5 steps is 100,000. 6 steps is 1,000,000 times stronger. So it's one of these really crazy ideas when you're comparing earthquakes like a 3 to a 9. Well, that's 6 steps on the Richter scale. So that's 10 times 10 times 10 times 10 times 10, and it's that much stronger. So there's some really interesting sort of facts that are on this chart. And Abby, to answer your question, yeah, big earthquakes will actually, they'll go around the surface of the earth several times. So if you can imagine an earthquake happening in Kelowna, it would actually emanate around Kelowna and travel around the surface of the earth, and they can come back and travel around again. And we can see this happening with really big earthquakes. It'll work its way around the world several times. If we look at the Richter scale here, anything under a 2, there's about 1,000,000 earthquakes a year on Earth that are under a 2, and you can't really feel them. They're quite small, generally don't cause any damage at all. They're very, very small. If you go up to a 3, this is when you start feeling earthquakes. So at about a 3 to 4, this can be felt, and it generally won't cause a lot of damage. You can see a lightning bolt here. If a lightning bolt were to hit the ground close to a seismic station, it would measure about 2.5 on the Richter scale. So that's a lot of energy being released, but it doesn't really have a huge impact on us. If you get up to like a 4 to 5, it says light property damage. So that's things like falling off shelves. Generally speaking, you don't end up with like structures actually being wrecked. A tornado carries about a high 4 in terms of energy. Then you get up into the 5, 6 range, you get moderate earthquake. That's when buildings start to break, like structures will start to crumble and foundations will break. If you're getting 6 to 7, this is considered a strong earthquake, and you're going to get into a kind of loss of life. So buildings start to collapse at that. 8, you get major impacts, loss of life. You can see some earthquakes sort of measuring in that area that you might be familiar with. One thing we're actually going to talk about a little bit later is Mount St. Helens eruption. So this was a volcano that erupted, and it actually measured just really close to 8 on the Richter scale. That much energy was released. So we'll look at why that was here in a second. The one that you might have been familiar with was the Fukushima the Fukushima earthquake that happened in Japan in 2011, which was a few years ago. It was really just below a 9 on the Richter scale, and that killed about 20,000 people. There was a tsunami that went along with it. And then you get up to the largest ever recorded was actually happened in Chile in about 1960, and lots of shaking and lots of damage. Basically, once you get above 8 to 9 to 10, every building will just get leveled, just flattened completely. So somebody last day was asking about nuclear bombs, and I think it might have been Alex, he's saying, will a nuclear bomb cause an earthquake sort of thing? So the bomb that was dropped on Hiroshima, the first atomic weapon used in war, measured about a 6 on the Richter scale. So if you think about that logarithmic scale, each step being 10 times stronger, the earthquake that happened in Japan that we looked at some of the tsunami footage, it was actually almost 3 steps up the Richter scale. So 10 times 10 times 10, 10 times 10 is 100. So the Fukushima earthquake was actually 1,000 times stronger, or the equivalent of dropping 1,000 nuclear bombs on that city. And then you go to Chile, which is another step higher. That's 10,000 nuclear bombs being released in a very short period of time. So this is why the Richter scale is kind of interesting. Each step is 10 times stronger. We're actually going to talk about another scale later when we get into chemistry. It's called the pH scale, which tells you how acidic something is. and it's also measured on a logarithmic scale like the Richter scale is. So I always find all this stuff quite interesting, and you can see the energy that's released over on the side here. You start in like kilograms of TNT, and then when you get up to the top here, you're talking about trillion kilograms, like an unfathomable amount of dynamite exploding. Even here, the atomic bomb of Hiroshima is about 100 million pounds of TNT. You do learn about logarithms in math 12, so you got a couple years to make it to math 12. You can't read this really well, but I found this super interesting. This first graph here on my right, your left, is a seismic reading of that was just outside of the stadium in Seattle. When Seattle 2 years ago won the Super Bowl, you can see some really crazy stuff happening. Seattle's known for having really amazing fans that create absolutely immense amounts of noise, and the actual stadium can shake. So you can see here where this is just kind of background noise, so like trucks driving by and stuff will give you this sort of thing. The ball was, hiked, so that means the quarterback had the ball. Marshawn Lynch, who's the running back for the Seahawks, made it through the hole. Then he hit this guy, and the crowd just erupted in noise. And then he scored a touchdown right here. And then the fans were going crazy. And then you can see a little blip here where they kicked an extra point. So pretty crazy stuff that, you put thousands of people in a stadium and you can get them to actually shake the building enough to be measured by seismic stations. Another thing that's happens in the news a lot is, this has just recently happened about a month ago, North Korea tested another nuclear weapon. And we don't have a lot of information that comes out of North Korea, so we can't just see what's going on inside of the borders of North Korea. It's a very secretive place. So how do we know when they test a nuclear bomb? How do we know it's just not some other type of bomb, or they're not doing something else? Basically, we can measure the strength of an earthquake that gets created by these bombs. So we have seismic stations all over the world. They're very, very precise, very, very accurate, and they can pick up the waves that get generated by it. So you'll notice that when we have an earthquake, you end up with a P wave and then an S wave, but when you get a nuclear detonation, you don't end up with that signature. So this is a seismic station just in China. They have their own sort of digital network, and each one of these lines is a different nuclear test. So you can see the first one, 2006, is this green line, wasn't a very big bomb, a very small nuclear weapon. And then in 2009, they tested it again, and you get the red line, so a bit of a bigger bomb. And then in 2013, you get another blue line, which is a much bigger bomb. And then just recently, I don't have the most recent seismic readings, but just last month, they tested another weapon. They stated it was a hydrogen bomb. Now, you guys probably don't know the difference between a hydrogen and a regular fission bomb, but anyways, hydrogen bombs are generally a lot larger, and the international community was really skeptical that they actually had the technology to create a hydrogen or a fusion bomb, because a lot of the seismic readings that they were getting weren't very big, or weren't big enough to indicate that it was a hydrogen bomb, but it was a regular fission bomb. So when North Korea acts up and bombs start going off, how do we know? Seismic stations. We can look at the amount of energy that was released, and we can say, this is likely this type of bomb or this type of bomb. So, pardon me. Some other interesting uses of seismic stations. This is another one. This was September 11 when the terrorist attacks happened in New York City. You can see this is just kind of continuing on in time, so each line is just a continuation of time. But you see the first impact where the first plane hit, and then the second impact's right here, measured as seismic stations. Nothing happens for a while, the buildings are burning, and then the building collapses, and you get this huge spike on a seismic reading. And then when the second tower collapsed, you get another huge spike. And This was actually recorded by seismic stations in the New York area. So some other interesting things come as a result of these seismic stations. You can measure events in history. So I just like to talk about everything sort of really interesting that happens on Earth, volcanoes, earthquakes, structures that exist. They always happen at plate boundaries. So the tallest mountain. Everybody knows what the tallest mountain is. Do you know how tall it is? Anybody know? Without looking it up, do you just know how tall the tallest mountain on Earth is? I don't see anyone typing, so I'm going to assume nobody has that piece of information memorized. I'm going to possibly turn your world upside down. This is the tallest mountain on Earth. Hear me out. You see this nice ocean here, some beautiful condos, and you have this nice little mountain in the background. Does anybody know what this mountain's called? This is the tallest mountain on Earth. Its name. Anybody know what it's called? Nobody's gonna even guess what it's called. All right, tough crowd today. That's okay. So Mount Everest isn't the tallest mountain. It's not even close. Everyone thinks Mount Everest is the tallest mountain on Earth, but it's not. Here is a sort of a look at the tallest mountain on Earth. This is actually somewhere nice and warm, and this is the large island of Hawaii. The big island of Hawaii is Mauna Loa or Mauna Kea is right here. You can see the peak of it is actually the tallest mountain on Earth. If you go from the bottom of the seafloor off the coast of Hawaii, and you rise all the way up to the top, this point right here, Mauna Kea, you end up rising about 9,000 meters. So when we look at Mount Everest is only about 8,000 meters. So it turns out that Hawaii is about a kilometer taller than Mount Everest, which is significant. So why do people think that Mount Everest is the tallest mountain in the world? You can see on the top of Mauna Loa, which is right next to Mauna Kea, we have all of these recording stations and telescopes and things like that. It's amazing all of the technology that exists up on top there. Hawaii is the absolute perfect place to do observations about our planet and to do observations about space. It's in the middle of an ocean. The mountain, the Mauna Loa and Mauna Kea, are actually really high, so they're actually above most clouds. So you can look at the sky at night and you can get great views. There's no ambient light around. There's no noise created or anything like that. It's a great place to measure things that are going on in the atmosphere because it's so far removed from civilization. It's right in the middle of the Pacific Ocean. So they record things like atmospheric CO2 there, because if the CO2 is that level in the middle of the ocean, it's going to be higher on land somewhere, because generally speaking, that's where the CO2 is being created. So Mount Everest is famous for being tall, but it's not that tall. Mount Everest is it's on this really thick plate. Where India starts crashing into the Eurasian plate, that plate is really thick. The plate's almost 6 kilometers thick. Mount Everest is only about 2 kilometers tall. So if you took the fact that Mount Everest only rises about 2 kilometers from that plateau, the Tibetan plateau, the Himalayas are, Mount Everest is just a tiny little mountain. Not big at all. So Mauna Kea is actually the tallest mountain on Earth. Everest gets all the credit though. This mountain is arguably taller than Mauna Kea as well. And it is taller than Everest, and you have to hear me out on this one. It's a bit of a stretch, but does anybody know where this is? I wouldn't expect anyone would know where this is. This is actually in Ecuador. It's nice. Is that an alpaca? Is that what that is? I always get alpacas and llamas confused. All right, so Earth is a sphere. Well, not really. Earth is spinning really fast. So when things spin really fast, they get a little bit wider and it kind of gets squished down. So Earth isn't a perfect sphere. It's called an oblate spheroid. And if you were to take the distance from the center of Earth, so the absolute middle of Earth, to the very outer edge, this mountain in Ecuador is called Chimborazo, and it's about 6,384 kilometers from the center of Earth. If you look at Mount Everest, if you measured its distance away, the top of Mount Everest, from the center of the Earth, it's only about 6,382 meters. And then Mount Rainier is also a little bit further from the center of the Earth. So Mount Everest isn't even the furthest from the center of the Earth. So you end up with Mount Chimborazo being further from the center of the Earth. So why is Everest actually called the tallest mountain? Well, it's the highest above sea level. Well, does that make it the tallest? I don't know. It's the furthest above an arbitrary level of where the oceans are. So how do we know the distance from the center of the Earth? We can look at Earth from satellites and figure out exactly how thick it is, and we know how it rotates. We can figure out the exact axis of rotation. We're really good at figuring out where the center of the Earth is. So anyways, when somebody tells you Mount Everest is the tallest mountain on Earth, the key here is it's the tallest. No, it's not the tallest. Mount Everest is the highest above sea level. It's 8,848 meters above sea level, but Mauna Kea in Hawaii is about 10,000 meters tall, or about 10 kilometers tall. And then if you were to measure from not an arbitrary place like sea level, but the center of the Earth, because Earth gets a little bit wider at the equator, this Mount Chimborazo is actually taller than Everest. So some interesting things, you can trick your friends with that. Another really cool thing I think is fascinating is Lake Baikal. It's in Russia. It's a tiny little lake, and it exists at a divergent plate boundary. Not one of the major plate boundaries that we look at, but just a kind of a minor fault that's happening here. And it's actually, it's a big lake, but it's not that big. You can see it right here in southern Russia, or kind of the eastern part of Russia. And it's at this divergent boundary. So if you look at a map of all of the Great Lakes, so you can see all the Great Lakes here. If we added up all of the water in the Great Lakes, it turns out that the lakes contain about 21% of Earth's fresh water. If you took an outline of Lake Baikal here, which is smaller than pretty much all of the lakes, it's smaller than Michigan and Superior for sure. This one little lake here, not little, this one lake has about 20% of Earth's fresh water. So if you added up all of the Great Lakes and you put them all together, they would fit in this one lake, almost 1% to spare. So pretty amazing. It's the reason it holds so much fresh water is it's so deep. It's about almost 2 kilometers deep, 1,600 meters deep. Pretty amazing place. There's some really cool pictures of it too online if you ever look it up. It freezes in the winter, and it's pretty spectacular. So the reason it holds so much water is just so deep. We're going to look at the earthquake activity in a second. I'm just going to continue on here, finish off the notes for you guys. There's a little bit of notes on the types of volcanoes. So we'll look at the 3 types of volcanoes, and then we'll look at that earthquake activity, and then I'm done. So 3 different types of volcanoes. The first one's a composite volcano. And these composite volcanoes generally form on volcanic belts. And the volcanoes that are around us right now are generally composite volcanoes. So you end up with a really sort of steep mountain, very jagged, layers of ash and thick lava. You get this really tall sort of cone shape. Magma rises to the surface, and it hardens, and it traps lots of gas. And that's a really big problem. All of this gas gets trapped in these composite volcanoes. Pressure builds, and they don't erupt like nice, beautiful volcanoes do in Hawaii, where you get these big lava flows. It's kind of gentle and peaceful. The lava flows out. They erupt by basically exploding, which is bad. And we'll look at that here in a second. Has anybody ever been to a volcano before, an active volcano? In maybe Hawaii, that's a common place, or maybe somewhere down in Central America. I went to one when I was in Costa Rica. It was called Mount Arenal, and it was pretty cool. At night, you could look up, and it was just shot chunks of lava out, and you could see them kind of falling down the sides. It was a pretty cool place. If you ever get to go to an active volcano, I'd recommend it. All right, so let's look at volcanoes in our neck of the woods here, and then we'll look at Mount St. Helens. So everybody kind of knows where we live here in the Okanagan, and down, if you drive to Vancouver, you end up seeing Mount Baker. So the circles are cinder cones or lava flows. So they show volcanic activity. The triangles are volcanoes that are either active or dormant. So most of the volcanoes in our neck of the woods are dormant. This is Lower Mainland Vancouver area. And then Squamish, just a little bit north of Squamish, is Mount Garibaldi, which is the largest sort of dormant volcano. It can be argued that it's active close to, a major center like Vancouver, and it's in Canada. Baker's closer to Vancouver, but it's not in Canada. So we're not as interested in it. So we have all these active, slightly dormant volcanoes that run up the coast. Remember, when you get these plates subducting, they go dive underneath this big Pacific plate because they're thin, dense oceanic plates. And basically the magma starts to rise up. And you don't get volcanoes right at the boundary. They happen inland a little bit. So we end up with this big chain of volcanoes running up our coast as a result of this plate subduction. So when you think of BC, you don't really think of volcanoes, yet we have lots of volcanoes in British Columbia because of what's happening off of our coast. So above me here this is an image of Mount Garibaldi. It doesn't look like your traditional volcano, right? It's really jagged. It's a basically really jagged old rock, and there's lots of gas that's trapped in there. So what happens when a volcano like this erupts? Well, in 1980, this is before I was born, we had a volcano in Washington State. I'll go back here a second. Mount Baker's right here. Just a little bit further into Washington State, a little bit closer to the ocean, is Mount St. Helens. So it's just right down here, Washington State, nice and close to us. Now, I wasn't born yet, but my parents tell me that when Mount St. Helens erupted in 1980, the ash cloud, remember this is in Washington State, it was big enough to block out the sun in Kelowna. So for a couple days, there was so much ash. It was kind of like Okanagan Mountain Park fire ash. You couldn't really see the sun. It was really dark for a few days. Now, Mount St. Helens, when it erupted, it didn't erupt nicely. It exploded. And when you talk about a mountain exploding, we're talking about an absolutely immense amount of energy. Remember the Richter scale that we looked at before? The atomic bomb at Hiroshima was, about a step and a half lower on the Richter scale than the Mount St. Helens eruption. So we're talking about almost 100 times stronger than an atomic bomb when this volcano erupted. So there's a video here. We're not going to watch the whole thing, and I'll just kill the sound because it's not really what I'm interested in showing you guys. But it's kind of like a 2-minute documentary on the volcano. So this is what it looked like before the eruption. Nice, beautiful, composite volcano, covered in snow, quite tall, kind of picturesque. Didn't really look that threatening, but they started to read some seismics recordings. There's some small earthquakes that happened, and they knew that something was happening. This is it after. So we're talking about a mountain here that basically erupted. So it's an active volcano, but this is kind of the kicker here. This is a time lapse in really slow motion. It's kind of been computer rendered. There's only about 4 or 5 still images. And the whole side of the mountain blew off. Like this happened within a few seconds. The image makes it look like it happened over a really long period of time. So this was, really instantly. A few people died. I forget the exact number. I think it was less than 50. It was around 30 people that were hiking near the mountain actually died. and the whole side of the mountain, I'll show you one more time, just let go, and it blew up with the force of almost 1,000 nuclear bombs. So we're talking absolutely immense amount of energy being released within a couple seconds. It continued to erupt for a few days, spewing this ash and smoke into the atmosphere. You can see it kind of doing that here. But unless you've ever been down to look at Mount St. Helens, you can't really understand how big this eruption was. So what I think this picture kind of explains what the point I was trying to make. This is a forest here that was right on the side of Mount St. Helens. Now, all of these trees, they're actually lying down and they don't have any branches on them anymore. So when the mountain erupted or exploded, it was the equivalent of several thousand nuclear bombs going off. And instead of the forest, just absorbing the impact, literally all of these trees are lying down flat on the ground, and all of the sort of brush that was on them, the pine needles and stuff, just got knocked completely off. So these trees aren't lying flat because of a windstorm. They just got knocked over by this volcano when it erupted. So that's the amount of energy. Imagine walking into a forest and all of a sudden something happens and all of the trees just get knocked flat. You can imagine like a really strong windstorm. You know how trees kind of bend a little bit in the wind? Trees are flexible. They're used to putting up with really strong wind. This was so much energy released, this explosion just knocked them all completely flat, just leveled forests. Square kilometers of forest just completely flattened. So I try to put it in words how much energy was released and how big of an explosion this was, but I don't think I can do it justice. So use your imagination on that. There's lots of really interesting videos on it. And also sort of documentaries and information. So if you're interested in it online, it's a great source. The second type of volcano, so that was composite. Composite volcanoes blow up. They get gas trapped in there. It's really jagged sort of rock. They explode. They don't erupt nicely. I mean, they do erupt nicely, but then they get plugged up and then they go boom and erupt violently. Imagine happening like one of those movies where an explosion happens, then sets off a wave and all the trees falling. Yeah, exactly like that, but it happens like that. It wouldn't be like, ding, trees falling, domino, domino. It'd be like, boom, forest gone. Kind of like just a nuclear detonation, just wiping things out. The movie that I was talking about last day, I looked it up, it was 2012. Remember the whole Mayan prophecy, the world was gonna end. If you watch the movie 2012, it talks about the supervolcano under Yellowstone Park erupting. So I had to look it up. I couldn't remember. And then there was another movie that came up that I think Anna actually mentioned was called Supervolcano that talked about the same sort of topics. So there you go. Shield volcanoes are the ones that you think about when you think about volcanoes. The magma rises to the surface, becomes lava, kind of flows out nicely, and it's kind of, a peaceful volcanic eruption. Magma rises up, kind of flows out, and you get these nice distinct layers making the volcano taller and taller. So these are sort of gentle eruptions compared to the composite volcanoes. This is the Hawaiian Islands, most of Japan. These are all shield volcanoes. That's why Hawaii is so tall, because it just keeps erupting, keeps getting taller, new layer formed. So we're talking about Mauna Loa, Mauna Kea, all the Hawaiian Islands, they formed this way. You don't end up with explosions. They're nice, gentle eruptions, and you can get close to them and look at the lava, and it's pretty spectacular, whereas a composite volcano erupts violently. Lava is magma that makes it to the surface of the earth. So when it's under our feet, it's called magma. When it makes it to the surface, it's called lava. So that like glowing molten rock, lava. It's rock. It's rock that's melted under the immense temperature and pressure in the core of the earth that gets pushed up to the surface. Somehow it manages to break through in a weak spot, like the Hawaiian Islands, or where you get subduction happening, it rises up. And it is rock that is liquid because it's so hot in the interior of the earth. So shield volcano, Hawaiian Islands is the best example of that. The last one, I showed you this picture already when we talked about rift valleys, but it was the best picture I could find. So the last one is rift eruptions. So we're talking about the Mid-Atlantic Rift and on east coast of Africa. And you get the plates moving apart, which creates a kind of a gap where magma starts to go. So you get really long chains of volcanoes. They don't get really tall because it's just kind of magma just oozes out. You don't get big mountains being formed. You have really long cracks that open up and magma just flows out. That's about it. Because those plates are slowly moving apart, each time magma rises up, it's making new land. So as the plates move apart, it makes new land. Plates move apart, it makes new land. There's no time for it to build up and get taller and taller and taller and taller over long periods of time. So rift eruptions won't generally create really tall mountains. I mean, they can create volcanoes that are a couple hundred meters tall, but we're not talking like thousands of meters like Mount Rainier, Mount Baker, like these big volcanoes, or Mount Fuji or Hawaii, which is almost 10 kilometers tall. New layer of magma gets taller and taller and taller until it's 10 kilometers tall. Started from the seafloor, 10 kilometers up now. Crazy. These rift eruptions just keep moving apart, so the new magma just keeps forming new land. Abby, the hikers you're talking about, the shaking that happened was small, and this was in 1980, so there wasn't like cell phones. You couldn't just like call up your friend and say, hey, you know, there's a little bit of seismic activity. They knew Mount St. Helens was an active volcano, so I don't want to say it would have been really common, but lots of earthquakes are always happening around volcanoes as magma rises up, trying to create new paths to rise out. You get lots of really small volcanic eruptions and lots of really small earthquakes. So it would be kind of common for small earthquakes to happen. Then it just started to, rumble a little bit more, and you just don't know. You don't know when it's going to happen. And then eventually it just went kaboom, flattened forest, mudslides, all of that snow cap on the top just completely melted. Huge mudslides, flooding all around, forest just destroyed, buried under meters and meters of mud, all that hot magma and all that snow melting. Just crazy, crazy stuff. All right, so there's your rift eruption. Those are the three types of volcanoes: composite, shield, and rift. That's basically all you need to know about that. That's it for section or unit 10, section 10.2. I broke it up into a couple days just because I think this volcano and earthquake stuff is really fascinating. So I wanted to kind of share a bit of that with you guys. Hopefully I can drum up some enthusiasm about it. There is a earthquake activity which is built into your course, and it's actually in the learning guide. So I want to talk a little bit about that. I didn't know how long this would take, so I'm just going to jump back to the course, and I have time now. So I was thinking, maybe I'll just give you guys a break and then we'll talk about it, but I can just get this done and we can finish early today. So this is unit 10 in the course, and we've gone through all of the stuff now, the video for continental drift, the continental drift notes. The plate tectonics inquiry was giving some people issues. If you have a Mac computer, I was reading that it doesn't work on Macs. So if you can get your hands on a regular PC for a few minutes, you could go through that. If you can't, just send me a message and we can come up with something else for you to do, or I can omit it. Let me know on that one if you're having issues accessing it. So that's what we did last day. Today we finished off features of plate tectonics, which is 10.2, and just below that is the virtual earthquake activity. So I'm going to open this guy up. It doesn't look spectacular, but it's really cool. At least I think it's cool in a dorky sort of science teacher way. It has a lot of writing and it's trying to explain things, and it's worthwhile to read through it and to understand how we measure the strength of earthquakes and how we know where the epicenter of an earthquake is, or the focus even. And this tells you exactly how this works. Now, the methods that scientists use are more accurate methods of the exact same thing we're going to do right now. So they use just really precise instruments that have very accurate readings. We're going to do the same sort of thing with just, we're more closely to estimating than a scientist would use. And of course, this is all done by computers now, but 50, 60, 70 years ago, before we had really powerful computers, people did this by hand the exact same way we're about to do this. So if you could open it up and we can go through it together, and I'll make sure everybody's kind of on track, because it can get a little bit tricky in a couple spots, but I think you guys should be okay. I forget what pages in the learning guide this is. Maybe we should look at that before I get too carried away. So this is page 14 and 15 of your learning guide. So if you have that nearby, you might want to fill it out as you go. All right, so what is an earthquake? We know what earthquakes are. We know what seismic waves are, so I'm not going to spend time talking about that. This is a seismogram, so we've looked at a couple of them, and these ones are showing earthquakes. So you have a really distinct P wave, and then it kind of tapers off, and then you get a really distinct S wave. So you get your primary wave and S wave. And I talked about the difference in time between the S and P, the primary and the secondary. Basically, you can tell how far away the earthquake is from you if you can measure the amount of time. You can also measure the amplitude of the earthquake based on how much this line sort of shakes. So we're going to use all of that information to measure the strength and location of an earthquake. So here we go. You guys have all this sort of background information that most people wouldn't have. So down at the bottom of the page, you can pick a location. You can pick San Francisco, Southern California, Japan, or Mexico. Doesn't matter which one you pick. The process is the same for all of them. So just pick a place you're interested in or maybe you're familiar with in terms of its geography. I'm going to maybe go with Japan. Why not? I like Japan. So you're going to just click the little button and then submit choice. And then it's going to take you to the second page. You'll actually have to scroll up. Everything's kind of happening up here. So it gives you a little map of the Japan, the Japanese sort of area, and it explains a little bit about how to measure from the P wave to the S wave, the amount of time between those things. And then it says view seismograms. So what you're going to do is you're going to look at a pretend earthquake that happened in the region you chose, and it's going to give you seismograms, and you're going to have to measure the distance or the difference in time between the P wave, the primary wave, and the secondary wave. And they're all essentially the same. I mean, the graphs are a little bit different for each of the four choices, but the process is the same. All right, so we have 3 seismic stations that have given us these seismograms. And we're going to measure the difference in time between the primary wave happening and the secondary wave happening. And just below it, it gives you a little box to put in the time you recorded. So right here. So you'll notice that at the very beginning of the P wave, it starts at time 0. So here's your P wave, you get that light shaking, and then your S wave kicks in right here. So I want to know the difference in time between the start of the P wave and the start of the S wave. Remember, the important idea here is these 2 waves began at the same time. It's the same event that's caused these waves to travel. But because that P wave is faster, it's going to make it to you before the S wave makes it to you. So if you can figure out the amount of time between the P and the S wave, you can figure out how far it is away. So let's do that. Looking at my graph here, I have 0, and then I measure along. Why is the P wave faster? It just is. It's a faster wave. I don't know if that's a great explanation, but that's the one I'm giving you, Alex. So we have 50 seconds here, and then we go up by 2. So 52, 54, 56. Looks like it starts at 56 seconds. So I'm going to put in 56 in the little box down below. And then I'm going to do the same thing for the next graph. I'm going to find the initial P wave, starts at 0. They've marked that for me. And then the S wave starts in here. So this is 40. This is 42. I'm going to go with 44. So just below it, I'm going to put in 44 seconds. Then the last one, it looks like this graph was not quite as close. The P wave and S wave is pretty small, so this could have been a long, long ways away. But I have my P wave starting here. My S wave looks like it starts at exactly 70. So I'm going to put in 70. And I'm just going to leave that for a second. If you have this running on your computer, I'll give you, just a minute here to measure yours, just in case they're different than mine, if you picked a different location. And if you're off by a little bit, it doesn't really matter. It's not going to ruin everything. So be as accurate as you can, but don't think like it's the end of the world. It's not going to say, this is wrong. If you're off by a lot, it might say like, hey, you might want to reconsider that. You guys are experts at reading graphs. I know that from math. All right. Do we need more time for those? We're doing okay. When you're done, when you've entered your 3 times, down below there's this button that says Convert SP Interval. So you just click that, and it'll take you to a new page. So this is just explaining a little bit of the background again. The P wave travels this fast, then the S wave travels this fast, and then the sort of SP interval is here. The closer you are, the closer they're going to be together. Just like if you're really close to a lightning bolt, the sound and the light will hit you at the same time. If you're really far away from a lightning bolt, like distance of 600 kilometers, that might be a bit extreme example for lightning, but the P wave is going to hit you, and then, lots of time later, you're going to get your S wave. So down here, we have our SP interval we've entered here. So we found these 3 different times. And then we're going to use this chart here on the left to figure out how far we are away from that earthquake based on the amount of time between the S and P wave. So if our SP interval was 56 seconds, looking at the first one here, I go 50, this is 55, and then 56, and I go across and down, that's 540 kilometers. So 56 seconds, 55, 56, I go down right here, this is 520, 540, so that's 540 kilometers away, based on the amount of time between those two. Now I look at 44 seconds. So I find 40, this is 45, so I go 1 below is 44. I go across to the line at 44, and I go down, and that looks like 425, I'd guess. And then my last one was 70 seconds, so I go way up to 70, I go across, and it looks like it's at 680, so 680 kilometers. So I put in all of those distances based on the difference in time between the primary wave and the secondary wave. And I have these 3 stations, and I know how far the earthquake was away from these 3 stations. Now, this is what I think is so fascinating, and if you've ever used triangulation before, you're familiar with this sort of concept, but imagine if I told you that, that I lived 10 kilometers away from your house. So you're thinking, okay, Mr. Borden lives 10 kilometers away from where I live. Would you know where my house was based on the information I gave you? If I said, hey, I live 10 kilometers away from your house, would you know where my house was? Would it be possible to figure out exactly where my house was? No. Because you could go 10 kilometers away from your house in any direction, so essentially you'd have one big circle where you knew that my house was, 10 kilometers away. You'd have the circle that is exactly 10 kilometers from your house. So my house would have to fall somewhere on that circle. Okay, if I told 2 of you now, I say, hey, Abby, I live 10 kilometers from your house, and Alex, I live 15 kilometers from your house. So you would both look at your houses on a map, you could both draw circles. Would you be able to tell where my house was based on those 2 circles? Would you be able to pinpoint exactly where it was? you run into a problem again. If I have two circles and they overlap, they're going to actually overlap in two spots. So you wouldn't know exactly where I lived, but you would know two possible locations because two circles would overlap at two spots. Now, what if I added a third person to my example? Yeah, so if I took Taylor and I said, Taylor, I live 400 kilometers away from your house, I live 15 kilometers from Alex's house, and I live 10 kilometers from Abby's house. Now you have three circles, and they're all going to overlap at one point. So at that point, you know exactly where my house is. That's what we're doing here. I'm telling you at these different seismic stations, you are this far away, 540 kilometers away from the first station. You're 425 away from the second station, and you are 680 from the third station. So this is what triangulation is. And remember when we talk about a triangle, triangulation is three. So you need three sources to find exactly where this earthquake happened. So here is what I was talking about. If I draw circles from the three seismic stations, so I have this one from Tokyo. I said it was whatever, 400 kilometers from Tokyo. The other one was Akita, which is way over here, so I know how far it is from this one. And then my third station, I draw another circle from it. I know that these three circles overlap at this point, which looks like it's really close to Kobe. So I know the epicenter of my earthquake is Kobe, Japan, and that is where the earthquake happened based on triangulation, based on how far you are away from those three seismic stations. So this is what happens when an earthquake goes off, or when North Korea detonates a nuclear bomb under a big mound of dirt. We know exactly where they detonated it. We know how big it is based on the seismic station recordings. So we know lots of information based on this stuff. So you can click here now. If your measurements were off, you can go back and remeasure them, but I have a feeling you guys are fairly accurate with your measurements. And then if I click view the epicenter, it shows me exactly where it was. So it kind of confirms my numbers. It checks my numbers with the exact values. So I said it was 56, it was 56. I said it was 44, it was 44. I said it was 70, it was actually 71. So if I guessed 70, my distance is going to be off by about 17 kilometers. But you can see that this is exactly where it is, and mine was fairly close. So if you're 1 second off for everything, that's fine. I mean, you're going to be really close. So that's pretty good. So that's how you measure where an earthquake happens. Your data, actual data shows up. And then you can compute the Richter scale measure. The learning guide doesn't have you do this, but since I'm here, I might as well just show you how this works as well. This is how we measure how strong the earthquake was. And your learning guide kind of ends at this point. So if you made it this far, you should be able to fill out your learning guide with no issues. If you keep going, we can do the Richter scale measurement. So basically, when you see the seismogram, the farther the needle goes, the more shaking there was. If you can measure the amplitude of the S wave is almost always bigger than the P wave. If you can measure how high it made that little needle shake, you can figure out the strength of the earthquake. So let's just jump to the next page where we actually measure it. Here we go. So if we know the distance in kilometers we are away from the earthquake, which we just calculated using the SP lag time, and we can measure the amplitude that the needle shook in millimeters, this chart where the line crosses this middle, so we could have a distance of like 700, we could have an amplitude of like 0.5 millimeter, so we draw a line between these things, and wherever it crosses this middle point, that's the strength of our earthquake. So if I went from like 700 down to 1 here, it crosses at this, about a 6. So we can use a chart like this to measure exactly where our earthquake is. So I'm going to measure the amplitude. You guys don't need to do this. It's not required, but if you want to continue on, you can. It just takes a second or two. So this is 50 millimeters. We have 60, 70, 80, 90, 100. So it looks like this one's 90 millimeters. So that was my first station, was 90. How high is this? This is 150. It's going up to 160. It looks like about 170 millimeters. It made that one shake. And then I go to the next one. This one wasn't very strong. This station was a long ways away. It was 680 kilometers away, but that's okay. We end up with it being, it looks like that's, 40, maybe like 38, I'm gonna guess. 38 millimeters. And then I submit it. So I've measured the amplitude of each of these. Sorry, Abby, the one I just did, it was Kobe, Japan, Kobe, was closest to the epicenter of that last one. So what this is going to do, it's going to generate a chart. It's going to take the distance away from the epicenter, which I calculated from that SP lag, and then it's going to take the amplitude that I measured in millimeters, and wherever these lines cross, the vertical line in the middle, this is going to be the amplitude of my earthquake. So even though this Akita was a long ways away, 700 almost kilometers away, it still had a pretty high measurement. And then my second one here, Busan, was about 550 kilometers away, and then the amplitude was about there. So they all should cross on one spot exactly, but they don't because my measurements were off by a bit. But it looks like it's about, really hard to see, it looks like it's about 6.8. So I would estimate the magnitude of this earthquake to be 6.8, where all three of those lines cross. I'm going to confirm my magnitude, and you can enter information if you want. It gives you a fancy certificate. And it tells you, if you just click the next, it tells you exactly how close you were on everything. So your S&P, the actual, and yours, so this was mine. I was good up to here. I got 71, which was close. My amplitude, I said it was 90, it was 81. I said it was 170, it was 201. I said it was 38, it was 30. It ended up that my errors all cancel each other out essentially, and it was 6.8. So there you go. We do it with computers now. We didn't always. That is how you measure where an earthquake's epicenter is and the magnitude of it based on these charts. And now it's just all done in computers almost instantly. As soon as an earthquake happens, computers talk to one another. They say, hey, did you measure that earthquake? Yeah, I did. It was this big. Okay, that means the SP lag was this, and this is where it was, and it just boom. Instantly, the computers know exactly the epicenter of that earthquake. Why is it important to know it instantly? Well, earthquakes can cause tsunamis. Earthquakes kind of radiate out extremely quickly, so you don't, once an earthquake happens, you can't warn people. It's already happened. But tsunamis happened as a result, and you can warn people of those because they travel a little bit slower. So that's Unit 10 done. We are done 1, 2, 3, and 10. And I asked you guys to be done Units 1, 2, 3 before the break. I want you to be done Unit 10 at the end of the break. I will tell you this one thing though. Over the break, I'm not going to be marking learning guides. I won't even be near a computer. So unfortunately, I won't have access to the course, and I won't be able to give you test passwords over the break. So this is why I have been saying for the last 2 weeks, you need to be done everything before we go for break. So if you haven't finished 1, 2, and 3 before Friday, then there will be no passwords over the break, so you just won't get that done. Unit 10, if you can submit it before Friday or Friday at the end of the day, I will get it marked and back to you, and you can do the test whenever you want over the break. I will be marking learning guides up until Friday, so whenever you submit them, I'll mark them, get the passwords out to you. So as long as it's before Friday, you're all good. Friday at about 3:15, I'm going to be really tired and not going to want to mark learning guides. But if you get them into me before 3:15 on Friday, I promise you I will get you a test password sent out as soon as I can. so Friday. I'm not going to look at a computer for 2 weeks because I stare at a computer screen all day, every day. I need a break. My eyes need a break. I'm not going to be doing schoolwork over the break. And I encourage you guys to work really hard up until Friday and get everything out of the way so you can relax over the break. I'm not going to give you guys any work to do over the break. I want you guys to enjoy time outside with your families, friends, whatever, but not doing schoolwork. Do it what it is you love. It's a break. It's March break. You won't need to get any work done over the break if you're caught up. I will open Unit 4 up. I'm going to admit I haven't really spent a lot of time looking at it. There's no module exam for Unit 10, Abby. So if you get Unit 10 handed in before Friday, awesome. If you don't, not the end of the world. 1, 2, and 3 don't get handed in before the break, that is the end of the world for me. There's really no reason you should be doing Units 1, 2, and 3 anymore. What should I do about assignments that won't open for me? What assignment are you running into issues with, Taylor? Is anybody else running into issues with assignments not opening? There was the one that we talked about, Taylor, with the plate tectonics. I sent you a couple emails about that, so if you could just read the emails, and if you have any other questions, just let me know. It should be pretty clear. Just do what you can. That's where we're at. Okay, all good. Check your email, Taylor. If you can do some of that, perfect. If not, I completely understand. That's where we're at. That's where we're going. I'll open up Unit 4. You should have Unit 4 printed off before the end of the break. So when we come back, we have class on, I want to say Wednesday, I think. We only have one class after the break, that first week back with science. You have Mrs. Ward on Tuesday and Thursday. So we only have that one class, and we're going to start Unit 4. So I don't want to have to talk about Units 1, 2, 3, or 10 until we start reviewing at the end of the year. We're done these things. We got to move on. It's time to get going for some of you. You're kind of stressing me out. You got to get this stuff done. If you are slow poking it through this, you just won't finish in time, and bad things will happen. So I don't want that to happen. I want you to kind of realize your full potential in this course. And for some of you, that means working a little bit harder than you have been. There's a Module 1 exam, which is the end of Unit 1, 2, and 3. So it's all of biology together. Your midterm in science will be on April 14th. We'll cover everything up to that point, and I'll make sure there's a clear cutoff when you guys are all aware of what's going to be on it and what's not on it. So midterm in science, April 14th, same day as your Heritage Fair with Mrs. Ward. Module 1 exam, you should get it done before Friday. I mean, if you're done Units 1, 2, and 3, it's just more of the same. It's not difficult. People took less than 20 minutes to write it, so it's not a tough exam or anything. It's just a few extra questions for the whole unit to kind of put everything together for you guys. So that's that. If you have any questions, if you have any concerns, if you're having issues, it is only Wednesday, so you have till Friday. Send me messages, ask questions. If you're having issues running into problems, let me know. I understand. I am a human and things happen. So if you're running into problems, let me know. But if you aren't and you don't have these things done by Friday, I'm going to be very, very concerned. So I'm going to leave you with that. I hope you guys have an amazing break, and I will see you guys in April, which is crazy. You get 2 weeks off plus a few days. So have a terrific break and enjoy yourselves and your families, and we'll see you guys in a couple weeks. Thanks.